Hi, welcome to this new webinar about power electronics. So good evening to you all, or good morning, depending on where you are on the planet listening to us. So while we wait for everybody to join in, because we are expecting around 34 people tonight, we will just again present ourselves and say hi. Gonzalo will join me again tonight as my co-pilot to answer your questions. Hi, Gonzalo.
Hello, good evening, Christian, and good morning for everybody in the South Pacific.
So today, as you will see, we will have a kind of a different structure because we are not using our LV-SIM simulator anymore, but as you will see, we will be using our physical EMS system, which will be presented in a moment. Again, if you're new to the GoToWebinar interface, you will see on the right that you have a handouts tab section that you can open up, and you will see that we are, oh, there was 2 files there. How come? Where is my second file? Okay, let me correct that right away. In fact, I was sharing my PowerPoint with you. It doesn't seem to have properly copied. There it is, 100%. There you go. So you will see there are 2 files that you can download while we wait for everybody to join in. Are the PowerPoint I will be using tonight and the datasheet of our EMS training system that we'll be using tonight for this webinar. So that's it for what's available there. You will also see the questions tab where you will input all your questions that Gonzalo will answer either immediately in written form or will pass to me to answer verbally so that everybody can benefit from the answer. And well, that's about it. In fact, and there is the chat box also where you can enter anything that is not a question. So please reserve the chat box for comments and things like that, or problems, technical problems you might have, and keep the questions for questions about the topic of the webinar. So yeah, well, I think we will start slowly.
Can we start with the polls?
Yeah, start with the polls. So I will have a couple of questions for you. Once again, for those of you familiar with our webinars, you will know that unfortunately, not all of you will be able to answer to this poll because of the technical problems with the GoToWebinar interface. But so if you click on an answer and it doesn't work, it's unfortunately not rare.
Okay, so, I'm seeing the polls coming in.
Yeah. This help us orient the presentation. So if most of you are not familiar at all, or not too much with the topic at hand, I will spend a bit more time to explain. If everybody was really familiar, I would spend less time on the theory. So as I can see here, most of you have some knowledge of it, or not at all. Not too many people are totally familiar with the topic. So this should be a
nice mix.
Yeah, this should be a good webinar where you will learn how to teach that with your students and also maybe grab a few new concepts. So thank you for answering this webinar. From this poll, sorry. The next one is for those of you teachers. If you ever had a chance to perform a lab with your students about power electronics, like we will do together tonight. Sorry, I say tonight, I should say today, because for most of you, it's morning now. I'm not sure that too many people are listening to us at 9 p.m. Okay, thank you for your answer. So it's about half and half. Well, more no than yes, so more people didn't have a chance to perform that. So I hope this will give you a feel for what it could be and what you could teach your students through such a lab. Thank you for answering. I now closing the poll because we will be starting the webinar just now. So welcome again for all of you who just joined in to our Power Electronics webinar. So tonight, if you attended the previous webinars we gave over the last 2 weeks, you will see that we have a different format because the last 2 weeks we were using our electronics lab simulator on the computer, and tonight we will be using the physical system that this simulator was based on, our EMS training system that I will present to you in a moment. So the reason for that is, as we told you in the previous 2 weeks, our LVSIM simulator does not support power electronics. And since this is a really hot topic that most of you want to be able to teach, we decided to give a webinar on the topic, despite the fact that it's not supported by the simulator, but the physical system. So for those of you lucky enough to have the system, you will be able to start right away playing with it. And otherwise, well, you will see the capacity of the system. Okay, so Power Electronics webinar. What will be the program for today? First, we will start with DC power electronics. So this is an introduction to understand what is power electronics and how to achieve it. So we will start with the simplest circuit of all, the buck chopper. Then this will lead us to the 4-quadrant chopper. Oops, Gonzalo, okay, you just closed my camera too. Okay, that's interesting. Let me bring back my camera here.
Yes, I am not seeing your screen either.
You're not seeing my, and probably nobody does. Thank you for telling me, but I don't know what was the problem with the camera. You just shut off my camera.
And I should not be able to do that.
Okay. So tell me when you see the screen.
Yes, now I'm seeing your screen and your picture, so now it's working right. Yep.
Perfect.
Go ahead.
Okay. Sorry about that. So yes, I was saying DC power electronics with the buck chopper and the 4-quadrant chopper, and this will lead us into AC power electronics with the single-phase Pwm inverter, and finally 3-phase Pwm inverter. Hopefully we will have enough time to perform this last exercise. All of these topics will be covered both in theory and practice. So we'll have 4 different circuits to test tonight. Well, in fact, 3 circuits for the 4 exercises. And this will allow us to discover some new tools that are available. So we will revisit the data acquisition and control interface module that you know from LVSIM, but now we will be looking at its physical version. Then our IGBT modules for chopper and inverter implementation. So insulated gate bipolar transistors, so the power transistors we use. And then our induction motor module. In terms of software support, we will be looking at the measuring instruments that you are familiar with, but now in LVDAC instead of LVSIM, and the chopper inverter function set that we will be discovering together. So you will see that all the exercises I am proposing to you today, are extracted directly from our manual. So that's why, and they are extracted from multiple manuals because we have multiple courses on power electronics, and that's why you will see that the exercise numbers are not sequential because I'm in exercise 2 of our DC power electronics volume. Then I might move to exercise 1 of AC power electronics. So don't worry about the numbering here. So the buck chopper, we will discuss what it is, how it can be implemented, and we will see how to operate it with a resistive load. We will see it hands-on with the system. The last portion of the exercise that is part of the manual will not be done tonight. So before diving into this, any questions or technical problems that are passed on to you, Gonzalo?
Not yet. We're fine right now. Everything under control.
Thank you. Can I ask you to turn off your microphone when you're not?
Yep, it's off.
Thank you. Okay, so let's start with the first circuit here. Well, before, in fact, diving in the circuit itself, let's say a quick word about power electronics for those of you not familiar with it. As you know, electronics was born in the 50s when the transistors were invented and starting to control basically the flow of currents, at first at low voltages because the transistors were low voltage, low power devices. But then over the years, we were able to develop high power transistors that were able to let currents of hundreds of amperes flow through. So this allowed us to start doing not electronics, but power electronics, so controlling the large currents and voltages using transistors. At the same time, these IGBTs developed in parallel with thyristors, which were meant for high power implementations. But nowadays, the power transistors are so good that they are quickly replacing all the thyristor installations that were there before. So as you know, a transistor is simply a switch that we can control electronically to let current go through or not. Well, in fact, it can do more than that, but when we talk about power electronics, basically we use it as a switch, okay? But a really quick switch that can be turned on and off really, really quickly and multiple times in a single second. So that's the capacity of the transistor that we will be using to implement all of our power electronics circuit. So what you can see here is the most basic power electronic circuit you can find, with on the left side a DC source that will provide us with a constant voltage. On the right side, a resistive load to which the source is connected. And between the two, we have a power transistor, an IGBT in this case, that we can turn on and off. So when the transistor is off or open like this, the circuit is open, no current is flowing, the resistance doesn't see any current nor voltages. Your microphone is not off, Gonzalo. I can still hear you. So it might be again GoToWebinar playing tricks with you. When the transistor is on, the circuit is closed, and then the voltage can reach the resistance and have a current flow through the circuit. So simply, we will use that to allow current and voltage to be applied and power to be applied to our resistive load. So which will yield something like this. So on the first graph, you see at the top here, the switching control signal graph. We are showing you the triggering signals that we send to the transistor to turn it on or off, okay? So you can see that we can repeat a sequence of on, followed by off, followed by on with our transistor. So if we do it in a cyclic way like this, we see that there will be a certain period for the time that elapses between the moment we first turn the transistor on and the next time we turn it on. So this will be our period, and then part of this period, our transistor might be on or off might be on for a longer or shorter time. So on the graph we see here, it's about on for half of the time and off half of the time. So this relation between the time the transistor is on and the time the whole period lasts, the whole cycle lasts, is what is called the duty cycle. The duty cycle of our application will make the ratio between the two here. So right now, if I am at half of the time on, half of the time off, we say that we have a duty cycle of 50% or 0.5, depending on how we decide to note it. Of course, when the transistor is on, as you can see, the voltage will reach. So the circuit is closed, so the voltage reaches the load. So here is the voltage at my load. And of course, when the transistor is off, no voltage at the load. Same thing for the current. Current flows when the transistor is on and no current when it's off. So what will happen here is that by turning on and off our transistor really quickly like that, we will be able to change the average voltage reaching our resistor, because basically the resistor does not care too much about the fact that the voltage is constantly flowing or on and off if it switches quickly enough. And quickly enough will be multiple thousand times a second. So I can turn my transistor on and off 1,000 times, 10,000 times, 20,000 times a second. So for the resistor, it will warm up anyway, because there will be a constant flow of electrons through it. And even if it's on and off, it will at that frequency, it will not see the difference. A good example of that is a heating element in your house for baseboards or for your water heater or in your oven. We could control the amount of power that we send to such a heating element by using power electronics like that. It's not used like that. We don't use power electronics in home appliances like that. It's done on a longer period, but let's say that would be a good example of where we could use power electronics like that to control the average power we send to the load. So right now, if I am at a duty cycle of 50%, basically the average voltage that will be seen by the load is half of the input voltage. So let's say that my source is providing 50 volt of DC voltage. Then with a duty cycle of 50%, 50 volt multiplied by 0.5 gives me an average of 25 volt at the load. And of course, if I make my duty cycle 10%, then it will be only 5 volt at the load in terms of average. So that's exactly what we will test now by setting up this circuit here using our EMS demonstrator that I have here in my office, in my home office. But before showing you how to connect that, I will present you two different modules that I will do it here on the screen. It's easier, and then you will see them in the console. So here is the module that you should be familiar with now if you have followed our previous webinars on LVSIM. This is our data acquisition and control interface module with the 4 voltage inputs, the 4 current inputs, high voltage, 800 volt, 40 amp current. So this is our power. These are our power inputs, and our low power inputs. So 8 analog inputs that can accept values between -10 volt and +10 volts. We will use these inputs also tonight to monitor the triggering signals, the switching signals that we are sending to our transistors. Then the next module I want to introduce you to is this one here. This is the main module that we use in power electronics labs. It is our IGBT chopper inverter. So as you can see, it is composed of 6 transistors that are connected in a gate like this, in a kind of standard configuration for transistors like this. And as you can see, we will be able to use only one of these, 2 of these together, 4 of these together, or the 6 of them together, depending if we want to implement a buck chopper, a 4-quadrant chopper, or a 3-phase PWM inverter, as we will see today. On top of that, you can see that we provide 6 discrete inputs to send triggering switching signals to these transistors separately. So transistor 1 input signal and all that, so that you can provide your own triggering signal. We will come back to that, but you could develop your own algorithm and input the switching signals to the transistors from these inputs here to control yourself the behavior of this IGBT module. But typically, we will be in our exercises using this DB9 input here. So we will connect a DB9 cable here to send at the same time the 6 switching signals to the 6 transistors in parallel if we need the 6 transistors to be controlled at once. And finally, you will see on the right side that the module is completely protected against all sorts of bad conditions, so overheat, over voltage, and over current. Again, our modules are all configured to be as student-proof as possible. And typically these modules, the return rate we get on these modules is really, really, really low, less than 0.2%. So they are really sturdy. They don't get broken easily. So let's now look at that in the real system. So this is the circuit that we want to build. So the same circuit I've just shown you, except for 2 different small differences. You can see that we have added a diode here. It's a freewheeling diode that I won't discuss tonight. This is off the topic because we will be using mostly resistive loads anyway. And there is the capacitor at the entrance to maintain the voltage constant at the input of our chopper. Same thing, this won't be discussed tonight. So we are mostly interested here about the source, the transistor, and the load, the resistive load that we see here. Okay, so now I will switch my camera so that you can see the system. There you go. I'm sorry if there's not enough light. I do what I can, but here it's 9 o'clock p.m., so 9 p.m., not o'clock, not 9 p.m. So not too much light in my office, sorry. So what you see here is our whole demo suitcase for the EMS training system. So you know now from LVSIM that this system can be normally is composed of a larger console that will contain multiple modules. This is a small version of it that makes it that we can transport to customer sites and demonstrate the capacity of the system. So you will see at the top right here the data acquisition and control interface that you're now familiar with. Just underneath the IGBT module, the transistor module I just talked to you about. Underneath that is the thyristor module that we won't be using tonight. We have another course that is built on thyristor power electronics. So this one will not be used tonight. At the top left here, you have the top right, sorry, you have the our composite load modules that is specific to our demo suitcase, where you have resistive loads, capacitive loads, inductive loads, and a few more capacitors and inductors for filtering purposes that are here. Underneath here is a transformer module we won't be using tonight, and finally our induction motor module right here. At the bottom is, I will just show it to you, is the power supply. So this is the power supply block here that will provide us tonight with 300 volt of DC output to feed our IGBT module here. So now I will show you the connections that I've pre-made here, and you will see that they reproduce what we see here on the screen and in the schematic. So starting from the power supply at the bottom I just showed you, we go to, from my positive power supply, I go to the input here of my chopper inverter. Okay, from there I want to go through the transistor, which is here, and from there to ammeter 2 here. From ammeter 2, I take this cable here to go to, this is crisscrossed, to go to my resistive load here. From the resistive load, I go back to the other terminal of my chopper here, as you can see. And then the rest is simply, so this is the outside loop, and the rest is all meters. So I have E1 that is connected in parallel with the source here. I have E2 that is connected in parallel with the load, and the ammeter I just presented to you. So we will be able to observe what is happening in our circuit. So I told you that the IGBT module was receiving its inputs on the DB9 cable here, but I did not tell you what would be connected at the other end of this DB9 cable, which I have in my hand here. Well, the other end is connected to our data acquisition and control interface. So that's where the control interface part of the name comes from, because it is this module that will be responsible to send the control signals to the transistors. How does it know which signal to send? Well, it's because I remind you that our data acquisition module is also connected to the computer through USB connection. So I use this USB cable that is connected to my computer, and I connect it to my data acquisition module here. So I will be able to control the signal that are sent to the signals that are sent to the transistors from this module that I will control from the computer. Perfect. I just turn on here the system, and I will switch to our LVDAC software. That is the equivalent of what you find in LVSIM, but do I have it open here? No, not yet. So we'll go to open it here. So yes, it is the equivalent of what you find in LVSIM, but it is here only as you see, LVDAC-EMS. It is the software that is meant to be used in parallel with the physical system, not the simulator. When you launch it, you have the choice of running in 2 different modes. Demo mode is always available, even if you don't have any of our equipment in your lab. You can use the demo mode to explore the capabilities of the software. And by the way, this software is downloadable for free from our website, and Gonzalo will copy in the chat box now the address, the URL for you to go on our website and download the software for free. This will allow you to test it in simulator mode, not simulator as in LVSIM, where we just generate fake voltages and currents so that you can watch something basically, but this is more to for you to evaluate all the different functions that are available with this software. Right now I am connected to my equipment, so I will use the connected mode here. And I will load a pre-saved configuration files to once again speed up the process of setting up everything. So I have simply created a file for the buck chopper configuration here. Any questions, Gonzalo?
Okay. Hello. So no,
Hello?
right now we have we have some questions, and I'm handling the answers. And I just paste, as Christian demanded, 2 links, so you can download the software that Christian is showing right now. And also, I had a question about the double fed induction generator. So yes, we are able to make exercises with a double fed induction generator, but not with the simulator, with the real equipment. So I also placed the link for the double fed induction generator modules that fit into the same system that we are working right now, that is the EMS. So you have several bunches of information to grab right now.
So yes, we have a complete course on the doubly fed induction generator, indeed. So now what you see, well, some of it is already familiar to you, so you might recognize our oscilloscope from the last couple of webinars, where we have our 8 inputs that we can configure to display what we want. Our meters, 18 meters that can display again whatever you want. So all of this is the same thing as in LVSIM, as you can see. The difference now is that I will be getting the data here not from the simulator, simulated data, but directly through the USB cable. I will get this data from my data acquisition module that I have just shown you. The buck chopper function here is the one we will be using. So I will introduce you to this window here. So you can see here at the top of the window that we are in the chopper inverter control window. So this refers to a set of functions that we provide with the software that will allow you to implement multiple power electronic circuit. Here is the complete list of functions that are available through this function set. So buck chopper, high side or low side switching, buck boost chopper, 4-quadrant, buck chopper and boost chopper with feedback, single phase PWM or 180-degree modulation inverter. Same thing for three-phase, 3-phase PWM inverter with constant V over F ratio, and finally DC motor drive with or without current control. So all of these make the object of a specific exercise, and it's all available to you right here. So right now we want to use tonight we will be using 3 of these functions together. And now we will start with the buck chopper high side switching here. So you will recognize the circuit I've just connected on that we had, for which we had the schematic, and that I connected on the module. Here are the controls, so I can control the switching frequency. So at what frequency are the transistors, well, in fact, in this case, a single transistor, at what frequency is this transistor switched on and off? So it's set at 1000 Hertz, so 1000 times a second on and off. The duty cycle control. So how will I control the duty cycle? Knob. So using the knob here, I will be able to change the duty cycle from 0 to 100. The duty cycle, initial duty cycle will be set to 0, and we don't use acceleration and deceleration time in this exercise. So perfect. I can launch here my function, and you will see that even if it is started, I still have no voltage at my load here, no current, and no, of course, power, simply because my duty cycle is set to 0. As soon as I start increasing this duty cycle, you will see in the oscilloscope that we are getting, 200, that won't make it. Whoops. Sorry, where is my channel 3? Channel 3 here. That's weird. Yeah, there's something wrong here. Okay, let me check my connections. There might be a bad connection, sorry. My ground is connected here, yeah.
Is your DB9?
Yeah, that's what I'm checking. I'm checking my DB9. I think it was loose, probably. There.
Yep, let's see if it works.
Something strange here, and it seems to affect only this this signal, because the other ones are okay.
Oh, your ground is in analog or in digital ground?
It is in analog on both sides. Okay. So anyway, that seems to be working for the moment, so I won't spend more time. If we have problems, we will see. So what you see here is our switching signal. It should be a bit more visible. Let's increase my sensitivity here without the DC offset. There we go.
Oh, that's okay.
So I have the triggering signal, the switching signal sent to our transistors here. And the duty cycle, as you see, is set to 16%, so which means that my transistor is on 16% of the time and off 84%. So let's make that an easier number. Let's say 20% here, like this. So at 20%, 20% of the time I will have the voltage applied to my load, which will have a current flowing through the load in blue here, and 80% of the time, no voltage, no current. And of course, this voltage here is the maximum voltage of my DC source, which is 325 volt, as you can see here. So 325 multiplied by 20% is somewhere around 64, 65 volt indeed. And you will see that this value changes as I change the duty cycle here. So lower average voltage, higher average voltage. I can go up to 120. I don't want to go above 120 because my resistor is rated for 120 volt voltage and about 30 watts of power. So this is at the limit of the resistor load of the demo unit. So as you can see, that works really well. I can control the average voltage at the output of my chopper just with the duty cycle here. And of course, I can also change the switching frequency. And you will see that even if I change the switching frequency, the voltage, the average voltage at the output will not change, but we will see in the oscilloscope that, of course, our cycles become shorter and shorter and shorter. But you see that it has almost no impact on the voltage output that we get there. So now I'm up to 10,000 hertz switching frequency. And it's much more interesting for me also, because in my ears, instead of hearing the 1 kilohertz whining from the transistors, now at 10 kilohertz, it's more bearable. It's higher pitch and much lower in intensity. So you can see that that's what a buck chopper does. It simply lets the voltage through and the current through on a certain portion of the time. Any questions, Gonzalo?
We're okay here in the questions. You can keep going. Everything looking nice and sweet.
Perfect, thank you. So now we will move to the next part of the exercise. I will shut off the power here, and I will go back to the PowerPoint here for the next part of the exercise, where we will discuss the 4-quadrant chopper. So the problem with the circuit we just looked at for the buck chopper is that we can only control the average value of the voltage reaching the resistor, but we cannot control its polarity. Okay, so we are stuck with if our source is connected to feed a positive voltage to the load, we are stuck with a positive voltage to the load. There is no way we can change the polarity of this voltage using our circuit. And since most of the time DC power electronics like that is used to control, for example, a DC motor, it's really good to be able, it would be really good to be able to change the polarity of the voltage, because this what controls the direction of rotation of our DC motor. So if I could change the with the power electronic circuit the polarity, I could change the direction of rotation of the motor, which would be really great. Which brings the 4-quadrant chopper that we have here. So when we're talking about 4-quadrant, here is the graph that we are referring to, and this is also the same thing when we were speaking last week about our 4-quadrant dynamometer. It's always the same thing. We are referring to this voltage versus current or torque versus speed graph, where we can see the different modes that the motor and generator can be in. So we can see here in the first quadrant, quadrant 1 here, that our voltage is positive, the current is positive. So in this case, our motor is drawing power from the source to be motoring. So basically, we are really in motor mode. Same thing in quadrant 3 here, when both the voltage and currents are negative, we are also in motor mode. It's simply that our motor is spinning in the opposite direction, if we're talking of a DC motor here. When we are in quadrant 2 and 4, you can see that the voltage is either positive with a negative current or voltage negative with a positive current. So when the voltage and the current are not of the same polarity, it means that we are in generator mode. So the current is flowing not to the motor, but from the motor. So it's reversed and to what we are expecting. And that's when the motor is behaving like a generator. So these are the 4 quadrants we are referring to when we talk about that. So why do we call the previous circuit a 4-quadrant chopper? Well, with the circuit that we will see now, you will see that we will be able to operate a motor in these 4 quadrants. So we would be able to generate a positive or negative voltage at the output of our circuit, and the current will be able to flow in one direction or the other, the same direction as the voltage or not. Here is the circuit. So as you can see now, instead of using a single transistor, we use 4 transistors connected in a H pattern like this. And again, they are connected between our DC source and our load on the other side. So these 4 transistors are paired up in 2 pairs, constitute 2 pairs basically. So transistor 1 and 5 work together, so they are on at the same time and they are off at the same time. And transistors 2 and 4 work together also. Also, these 2 pairs are complementary. So when these two are on, these two are of course off, and same thing when these two are on, these two are off. Perfect. So let's look at what the current does if Q1 and Q5 are on while Q2 and Q4 are off. So the current leaves the source here, goes through Q1, goes to the load here on the right, comes back through Q5 and back to the source. Perfect. Now what happens if Q1 and Q5 are off and Q2, Q4 are on? The current goes like this through Q2, goes through the load, but you see that now I will be traversing the load in the opposite direction. So now I apply a negative voltage to R1 and back to here through Q4 and back to the source. So as you can see, when Q1 and Q5 are on, I present a positive voltage to R1 and a negative voltage when it is Q2 and Q4 that are on. So what does happen if I set the duty cycle of my transistors here to be at 50%, which means that 50% of the time I send the positive voltage of my source, let's say plus 50 volt, and the other half of the time, the other 50%, I send negative 50 volts, so minus 50. So, well, of course, simple arithmetics, 0.5% 50 volt, 50% at 50 volt, 50% at minus 50. This yields 0 voltage as at the output. So the average voltage would be 0. And then if I bring my duty cycle above 50%, I will have a voltage that gets more and more positive. And if I decrease my duty cycle below 50%, I will get a DC voltage that it gets more and more negative, the average. So I am able to control not only the polarity of the voltage, but the intensity of this voltage with such a circuit. And that's what we will test now. That's what these graphs show here. This is the equation to calculate the output voltage based on the duty cycle of transistors Q1 and Q5. Don't have to dive too much into this equation, and let's get into the hands-on part of the exercise here with this circuit. So this is exactly the same circuit I've just shown you, except for a few things. We have added 3 voltmeters to be able to measure the voltage at 3 different places. We have added, still our ammeter to measure the current in the load, and we have added some inductors and capacitors here to act as a filter at the output of our H bridge here. So as you can see, with these inductors and capacitors, I will be able to filter out the high frequency components that are contained, as we will see with the oscilloscope, in the voltage output of an H bridge like this. So let's get to the connections of that. So I will now need to do modifications to the circuit. I will drive you through these modifications, but at the same time, I will ask Gonzalo to answer any questions you might have while I do this here. So let me switch the camera so you can see what I'm doing.
Yep, so I'm here to answer any questions. Up to now, we have several questions that have been asked, most of them administrative, except for the one of the double phase induction generator, and if we can do this kind of exercises with the simulator. So these kind of exercises that are involved in power electronics, we cannot do them with the simulator yet. We know that the modules may become available in the future, but nowadays we can just do them with the physical module, as you see. So now we can see that Christian is making our connections.
Yeah.
Using the demo case.
So as you can see, I still have my DC source connected here that comes to the input of my H bridge here, my chopper inverter, a 4-quadrant chopper circuit. And out of there, I want to come out of these 2 terminals here. So this is the terminal between transistor 1 and 4, and this one is between transistor 2 and 5, just like in the circuit you can see. So this point here will go to the inductor that is here. So that's what I will be connecting now. So from here to my inductor, which is a 2 millihenry inductor, just like in the picture. From the inductor, I want to go to the capacitor. So from the inductor to the capacitor. And at the same time, I want to go from the inductor to the ammeter. Input of ammeter 3 here. And from the output of ammeter, I'm going back to my resistor. So from here, I go to the, whoops, in fact, I already have a cable connected there. So from ammeter 3, I go to the resistor, as you can see here. And from the resistor, I go back to the terminal here between the transistor 2 and 5. Sorry, I have a small difference here between the circuit here and the one you see there. There are 2 inductors in the circuit you see in the schematic. Unfortunately, in our demo case here, we have a single inductor of this value, so we have to do with a single one, and that's why you will see that our filter is not as efficient as it should be, but still it will show you how well it could work if it was perfectly connected. And here, finally, I'm missing the last point. The other end of my capacitor needs to be connected also at the same point here, which I do now. And then I only miss my 3 voltmeters. So E1 is again connected in parallel with the source. So from the source, I go to E1 like this. E2 is connected at the output of our H bridge. So right here, E2. And finally, E3 is connected at our load. So the top of my load is right here. So I will connect right here for my E3. And the other terminal is shared with this here. So I can connect it right here. Like this. So I make sure that my resistor is at the proper value, 1200 ohm. That does not fit, in fact, what's there because I don't have the same voltage at the input. My capacitor is set to 4.4 microfarad, which is the closest I have to 5 microfarad of the circuit. And my inductor doesn't have any control. Good. Let's start the power here and go back to our LVDAC software. So here in, LVDAC, here. So I will again open a new configuration file. Here LVDAC tells me that it has lost connection with when I shut off the power. So I just tell it to try reconnecting, which it does automatically. Then I will open my next configuration file. For 4-quadrant chopper here. So what we will see now in this next exercise is that I will be able to, yes, again, control the amount of voltage I'm sending to my load, but in a really different way, because we will be able to change its polarity, as we will see. I will connect a few more cables to be able to monitor here my control signals that are sent to the transistors. So the 2 pairs of transistors receive the complementary signals that I will be monitoring here on my analog inputs. This here, so you can see now that the function I'm using is the 4-quadrant chopper instead of the buck chopper. And I have my meter set here to be able to observe my voltages perfect like this. So the 4-quadrant chopper, you can see the schematics, same one as we just did, the same kind of control, the switching frequency that I will set now at 2000 Hertz, the duty cycle control. So we saw in the previous exercise that I was controlling the duty cycle with the knob. Here, instead of using the knob, I say take the signal that comes in onto analog input 1 that is a signal that varies between -10 and +10 volt, use this signal as the duty cycle control. Okay, and this signal comes right here on the module. So you can see that I have a cable that comes out of a analog input that I have here at the top and goes to analog input 1 here, which corresponds to what is set here. So where does this signal come from, this analog output? Well, it's simply a simple signal generator that we provide, and we take the output of this signal generator to feed this analog input. Of course, you could use any signal generator that produces a signal between -10 and +10 volt to feed the input of the duty cycle control here. So that's why we provide it this way. And finally, the other parameters are not of interest for right now. So what this means is that since this is my command knob here that controls the amount of voltage present at the analog output, okay, I have set it to produce a voltage between -4 volt and +4 volt to respect my the rating of my resistors. I don't want to go above 120 volt. And with this knob here, I will control the voltage that gets into here, that in turn controls the duty cycle. So let's start that so you can see how it works. So I start the function here. And you can see that when I launch it, even if I'm producing a voltage of 0 here, so 0 volt, which means that I am sending a duty cycle of 50. In fact, in this case, here I have a duty cycle of 50, as you can see in the window here. Even if I have that, we still have lots of signals displayed here. So the first signal you see here is the E2 signal. So it's the voltage at the output of the 4-quadrant chopper. So as you can see, it is half of the time on, half of the time off. So half of the time, in fact, positive, half of the time negative. Do you see the scale here? 500 volt per division. So half of the time 300 volt, half of the time -300 volt, for an average voltage of 0, as you can see in E2 here, which is the voltage at the output. And these here at the bottom are the switching signals sent to the 2 pairs of transistors. So as you can see, when one is off, the other one is on, and vice versa. Perfect. So now let's increase the duty cycle by playing with this voltage output here. So you can see that using this knob, I control the voltage, the duty cycle here. As I increase the duty cycle, like that, the average voltage at the output increases. I'm now to 94 volt of average voltage. And as you can see, I'm now much longer with a positive on this one than on this one. So which yields this higher voltage, higher positive voltage. My current here in the resistor, why do I get this? Channel 2. I know, sorry, it's E3. It's my voltage. Yes, sorry. It's the voltage on the, but that doesn't make sense. Again, I might have a bad connections here. Right here. This is good. There's something fishy with the circuit. I think I have done a bad connection somewhere, but since time's flying, I won't have time to look at it. We'll try to change it on the next circuit. So basically, anyway, what I wanted to show you is that we can control the intensity of the voltage at the output, and if I decrease my voltage here to bring a duty cycle below 50%, like I'm doing now. So you can see that now that I am below 50%, my average voltage at the output is now negative. So you can see that with this knob here, I can have my average voltage at my resistive load vary between negative, positive, negative, positive. So can you see that if I am able to do that quickly enough, switching from positive to negative, I should be able to produce a sine wave that will vary between -120 volt to +120 volt cyclically generating a AC voltage at the output of a bridge that is fed DC current. And that's the next step, using a 4-quadrant chopper like that to produce AC output. And that's what I will do now. So if we go back to our PowerPoint, we'll see that the next exercise is about, that's it, generating basically a sinusoidal voltage at the output. How will we achieve that? Well, really simply, as you saw, I could have generated a semi-sinusoidal signal if I was controlling the knob properly. So instead of using the knob to send the signal for the duty cycle, we will use a sine wave, a pure sine wave, and it is this sine wave that will control the duty cycle of our transistors. And this way, we are sure that what we will get at the output is also a sine wave, but a sine wave that will be much higher in voltage. So with a signal that varies between minus 10 volt to plus 10 volt, we will be able to generate a voltage that varies between minus 300 volt to plus 300 volt at the output of our bridge. So that's what we will do now. With the software. So the only thing I will change here is that I will change my analog output here to be, instead of being controlled by this command knob, I will control it with a function generator. And again, you could use any function generator you have in your lab to generate this signal. I control its frequency, 60 Hertz, its amplitude. Again, I don't want to go above the rating of my resistor, so I limit it to 3 volt output. And I will just launch it now. No, sorry, not this one, but this one here. So, yeah, that's really unfortunate here. Okay, so now I will change my time division here to go up to 5 milliseconds per div. And there you go. So you can see that right now I have, I zoomed out a lot to be able to see all the triggering signals, multiple cycles of the triggering signals. If I do a single capture here, it will be easier to analyze. So you can see that when we are at the positive peak of our sine wave here, if we look at the corresponding triggering signal, you will see that, well, in fact, it's not the triggering signal. This is the output of my H bridge, sorry. But you can see that to this peak here corresponds the location where all the pulses are wider at the top, so in the positive half of the cycle, while the negative portion of my sine wave here correspond to where the pulses are wider at the bottom, so in the negative half of the cycle. So this is how there is a direct relationship between this and this. So you might wonder what's the difference between these two signals. This is E2, the output of my chopper before the filter, and this is E3, the output after the filter. So you see that the work the filter is doing, it is removing all the higher harmonics to produce something that is much closer to a sine wave. The best way to look at these harmonics is with our harmonic analyzer. So let's turn on this guy here. So our harmonic analyzer allow you to observe the harmonic content of a signal from. So let me maybe bring that down a little bit. I don't know if you hear the whining sound I have in my office here at 1000 Hertz, and that's the problem with 2000 Hertz. That's the problem of dealing with these frequency. I will leave it there to be able to observe on the oscilloscope properly. Here, my harmonic analyzer, I can set the frequency of the fundamental, which is 60 Hertz in my case, because I'm producing 60 Hertz here. And I can control the number of harmonics I want to observe, which signal I want to observe, so E2 in this case, and how I want to display the harmonics. So you can see from here that I have my fundamental at 0 Hertz, my DC component, and then I have a high peak around 33, 34, the 32nd, 33rd harmonics. Where does that come from? Well, if you take 2000 Hertz, which is my switching frequency, divided by 60, that's exactly what you will get, 33 Hertz, which is the frequency of the harmonics we get here. If you want to see if we can change that, let's bring that up to 2400. And you will see that now our harmonic is in fact at, oops, I just went above 2400, like this. And now you can see that the harmonic is exactly at the 40th harmonic, 2400 divided by 60. So of course we don't want, so this is the harmonic content of our E2 signal right out of the chopper. If we want to get rid of these high level harmonics, we have to look at E3 after the filter. And you will see that the filter has quite a good effect on removing the high level harmonics. But again, since my filter is not complete because I'm missing an inductor, I still have this high component here. But if we had the 2 inductors as in the real system, I would get rid of totally all of these higher level harmonics here. And this is the distinction in harmonic between these 2 signals here. So any questions before we conclude this webinar? In fact, I have one last exercise. If you can stay 10 minutes, 5-10 minutes longer, I will show you how we can control an induction motor by generating a 3-phase output out of a chopper like that, of an inverter. But first, do you have any questions?
Yes, we need here a very short explanation. Okay, the question is, what is the harmonic? The question arrived in the middle of your explanation about the harmonics. Okay. So what would be a very easy and quick explanation about the harmonics?
Harmonic is simply a multiple of a base frequency, okay? So here my base frequency is 60 Hertz. The first harmonic will be 60 Hertz multiplied by my second harmonic will be 60 Hertz multiplied by 2, 120 Hertz. The third harmonics will be 3 times 60, etc. So these are multiples of the base signal. And we find that everywhere in nature. So for example, in the sounds, when you hit a piano note, for example, it contains the fundamental frequency, which is the note we hear. And then lots of harmonics above that, multiples of this base frequency that gives the richness of the sound of the piano and all that. So this is from the sound perspective. From the electronics perspective here, it's simply that if we look at, and we can look at it from a mathematical point of view, that any signal can be represented by multiple sine waves of multiple frequencies added together, and the frequencies of the sine waves that need to be added together to produce any waveform are all multiples of the basic frequency. So these are the harmonics. I'm sorry, this is a really high level. It's kind of a complex topic. By the way, you will see here, I will switch to 20,000 Hertz. And if you hear the whining sound of my transistors, you will see that it disappears. Boom, it's not there anymore. And now you can see that in our harmonic analyzer, we don't have any.
My dog starts crying, I don't know why.
Yeah, can you imagine me in my office here? So just sitting beside the transistor module. And by the way, that's the reason also we use typically really high switching frequencies for these power electronics devices, so that they don't annoy the human operator like this. And now, of course, if I was to switch back my oscilloscope here, in fact, the frequency is so high that the oscilloscope is not able to display the discrete. I have to zoom in to be able to start seeing again the discrete peaks on these on this signal, as you can see. But anyway, so any other question? No? So let me just introduce you, for those of you who can stay. I will introduce you to the last exercise I wanted to do with you. It's really quick to connect. I will do it in 1 minute. So it is this one here. a 3-phase PWM inverter. So as you can see, in fact, the circuit I will be using is this one. From a DC source, I will feed a bridge made up of 6 transistors, the output of which I will have 3 outputs out of that. Each output will correspond to 1 phase of a 3-phase signal, and I will be able to feed a 3-phase load that you can see here from this 3-phase output. Here in the schematic, you see the 3-phase load is composed of any load that might be three resistors connected in Y. In my case, I will be using an induction motor as my 3-phase load here. And since I am using a motor, I won't need a filter because the motor has itself a filtering effect. So I will be able to get the output of my chopper directly, of my inverter directly to the motor. Yes, Gonzalo?
Yes, there's a small question here about why we have so much noise in channel number 2.
Okay. Well, in fact, it's not noise. That's it. It is the high frequency component of the harmonics that the filter is not able to remove. Okay. So here we don't see them because I'm not my sensitivity here is not high enough, but let me move my sensitivity higher here. You will see that we still have lots of higher level harmonics, and these harmonics constitute all of these peaks, all of these ripples that we see on the sine wave. So it's not noise. Well, it is noise, but it is noise that we know the source of. It's the noise that is created by the high level, the high frequency switching of my transistors here that generate these high level harmonics. So that's why it's important at the output of a circuit like that to have a filter, a good filter, to get rid of these harmonics, to feed a purer signal to our load.
Perfect.
Good. So let me connect just this circuit here. I will bring it back to the front here. So this is the circuit I will be connecting now. This one here. So if you want to follow me on the system here, I will
Christian,
quickly.
can you unzoom a little bit your screen? We're seeing just half of the circuit.
You only see half of the circuit.
Yeah, your screen is very zoomed out.
Well, I don't. Is that? Have you seen the whole presentation like that? Because
No, it's just now.
Is it okay now?
Yeah, we're seeing your PowerPoint, but only basically half of it. We don't see the full slide. We see just the first upper 3/4 of the slide.
Okay, let me stop sharing my screen and reshare it. Maybe it will fix the problem. Is it? No, still not better?
No. Maybe you can shrink a little bit your PowerPoint window and it will fit in the screen.
Yeah, if I was to know. So which way should I go? Upper left, lower right?
Upper left. There.
Like this?
Yeah, now we can see the full diagram.
Perfect. Sorry about that. Weird. Okay, so I'm just disconnecting here what I don't need. Which is almost everything. I won't be connecting any meters to observe what's happening. We will just look at the motor spinning and, well, maybe just measuring the current in one phase. So here is still my DC input to my bridge out of phase 1. I will go to the ammeter 1 here. And from ammeter 1, I'm going to the first phase of my induction motor here. And then the other 2 phases, I will not be measuring their current. I will go directly from the output of the inverter to the corresponding phase. So output 2 to phase 2, output 3 to phase 3, and here it is. So from here, I'm still connected to be able to watch the signals, the triggering signals sent to the transistors, and that's it. We should be able to have our motor spinning. So going back to LVDAC, reconnecting. And I will change here my function that I'm using with my chopper inverter control window here. I will simply switch now to, from 4-quadrant chopper, I go to 3-phase Pwm inverter, constant V/F ratio. The reason I use that is that this will allow me to modify the frequency while keeping the current constant in my motor, but because it will decrease the voltage at the same time as the frequency. Perfect. 1000 Hertz. I want a frequency of 60 Hertz at the output. My knee peak voltage here, I will set it to 50 because I don't want to overload the motor again. And that's it. I'm ready to go. I can start that. So the view you have on the motor, you might see that there is a small sticker at the top of the motor that will allow you to follow it when it spins slowly. Now I will start it. It will start really fast. Okay, so you can't see anything for the moment. The motor is spinning, but you can't see it. But now I will decrease the frequency here, output of my motor, just like you would do with a variable frequency drive. So as I decrease the frequency, the motor spins down. As you can see, it becomes slower and slower. And if I make it slow enough, you will see it spinning. So you can see now that my output frequency is at 5 Hertz, and now my motor is spinning really slowly. So basically, this shows to the students how to implement what happens inside a variable frequency drive. What is happening in there? Well, that's exactly what is happening. Of course, here I'm not going through the theory with you, but the whole course goes through this theory in details of the different signals sent to the different pairs of transistors and how they mesh together to produce 3-phase output. So the students really learn how this works. And of course, if I want to increase the speed of the motor, I just increase the frequency, the output frequency of my inverter here, and I can even go above 60 Hertz, 72 Hertz now for a speed of 2100 approximately. On the oscilloscope side here, in fact, I'm not observing the right thing. I just want to show you AI1, AI2, and AI3. So we'll just change that to AI1 here, like this. We'll put that 5 volt per div also. And I will change my time window here. So you will see that if I stop the capture, that we have 3 triggering signals sent to the 3 pairs of transistors that are complementary to one another. In fact, they are phase shifted by 120 degrees to one another to be able to generate this 120 degree out of phase, the 3 signals that are 120 degree out of phase out of the inverter circuit. So this is a really quick introduction. Again, the complete course goes through all of that in lots of details, but this gives you an overview of what can be taught with this circuit here, this system with power for concerning power electronics.
Yes, we have a last question that we may need to switch back cameras. Is Dr. Rui from the University of Sydney. She would like to see in detail your connection between A1 to control the transistors in the DB9 connector. So will be the control knob, the analog output to the analog input.
Okay. Yes, I will bring for this purpose, I will bring my camera closer. Sorry for the, I don't want to make you sick, anybody. I will just move the camera slowly. Okay, so we can see here that we have a analog output. We have two analog outputs, in fact, okay? And again, this is just a convenience we provide to you because it's like having two outputs of a signal generator that can be controlled separately. So you could generate a square wave out of this one and a triangular wave out of this one, or sawtooth or sine wave, whatever, or constant signal. So these are outputs that you might get from any signal generator. And they are controlled from the software, as I've shown you. What comes out of here is controlled in the software. And then you can take these outputs to feed any circuit you might want, or in this case, I was using the analog output 1 to feed the analog input 1 here. This input here, analog input 1. Which in the software I said that the control signal for the duty cycle would come in. So this input here is used as the control signal to control the duty cycle in the function of the 4-quadrant chopper that I've shown you. So since the software does not allow you to use any other input, you have to connect it to analog input 1 here. So again, I am using my own signal that I generate from my generator, but you could use any signal generator to feed your control signal here.
Perfect. Thanks so much, Christian.
You're welcome. So thank you for your patience. Again, I went overboard, but there is so much to be said with this this circuit here, or this system. So thank you to have been patient and wait for the end of the presentation. Hopefully this will have been instructive to you. So don't feel shy to provide us with your comments, your questions, your suggestions for additional topics, because Gonzalo and I will be continuing doing these webinars for some time still. So if you have anything to suggest, it will be our pleasure to, if we have enough demand for a specific topic, to build a webinar on this topic. So again, thank you, Gonzalo, for your great help. Now we'll be able to join our wives in our bed.
Yeah.
and let everybody in Asia Pacific spend a beautiful day. So hopefully we see you later this week for a webinar on process control using our LV ProSim software simulator that will allow you again to teach another topic remotely to your students, process control, using one of our simulators. Thank you, Gonzalo.
Thanks so much, Christian. Good evening for you and good morning for South Pacific and Asia.
Exactly. Have a good day. Bye-bye.
Bye-bye.